I was watching this After Effects tutorial by Video Copilot the other day, and what caught my interest was this polar coordinates tool in the software. And I thought, wouldn't it be cool if we recreate this effect in 3D with Houdini? In this tutorial, we are going to create our own polar coordinates tool in Houdini, after which we will go through some examples of the tool in action to create various effects. I've added timestamps in the video description if you want to jump straight to the effects portion. I also put the finished tool on Gumroad if you just wish to use the tool without having to create it. Now let's get started. A brief explanation on what the polar coordinates mean. Imagine a circle. To find the location of a point on this circle, we can use polar coordinates. What it does, it specifies the radius of the circle as well as the angle of rotation. Looking closely at the diagram, we can also draw a straight line and use Pythagoras' theorem to find the Cartesian coordinates or the xy coordinates that we are familiar with. In this way, we can convert one coordinate system to another. Now taking one step further, notice the purple line which represents our point that has been previously plotted. We rotate the line to get spherical coordinates of the point. The second rotation angle that we've just done is called the azimuthal angle, and the previous rotation angle is called the polar angle. Their terms are interchangeable depending on what context, whether it's mathematics or physics, you are using the system with. For this tutorial, we'll settle on this naming convention. However, we aren't going to do proper mathematical conversion, but create our own custom rules by studying the effects in After Effects. So, what the polar coordinates tool does in After Effects is that it converts a line into a circle. We can play with how much it blends from a rectangle to a circle. And as you can see that when the line travels down the screen, the circle gets bigger. Taking some screenshots from After Effects, and with a little bit of reverse engineering, we start to notice certain patterns. As the line moves down the screen space y-axis, the radius of the circle gets bigger. Looking at the last two images, it seems like the screen space x-axis represents the angle of rotation, where we can remap the x-axis from the left to the right of the screen to a range between 0 to 360 degrees of the circle. With that logic, we can also apply the same rule to our z-axis in Houdini to get the other angle of rotation, so we can create our spherical coordinates. With theory out of the way, let's try implementing this logic in Houdini. So in Houdini, let's drop down the geometry node and rename it to Polar Coordinates tool. We are going to create a line as our test object. And for now, let us point the line towards the x-axis. I'm going to hide the origin nome so that it doesn't block the view. And let's add a null, call it input, and create a subnet out of it. We are going to create a tool that you can later convert into a HDA so you can reuse it in the future. I'm going to call my subnet Polar Coordinates tool, and I'm just going to hide these parameters because I'm not going to use them. I'm just going to drag in some parameter sliders first, as we are going to use these sliders later to add more functionality to our tool. So, what we are going to do first is to find out our min and our max values for our x and z axis. We then get our current points and remap each point's x and z values to the minimum and maximum that we've found before. This would in turn return us a 0 to 1 value. With this new normalized value, we can then remap it to 0 to 360 degrees or whatever maximum rotation you allow it. Using an attribute promote, we promote our p value from point to detail. We set the promotion method to maximum and rename it to max_p. We copy and paste the node and do the same thing, but change the method to minimum and rename it to minimum_p. Now let's do the remap. Drop down the point wrangle and let's get the maximum and minimum p values using the detail function. We then fit our p.x to the minimum_p square bracket 0 and maximum_p square bracket 0, where square bracket 0 represents the first index of the vector, which points towards the x value of the vector. Let's do the same for the y and the z-axis. Although we won't be using the y value, but I'll just do it just in case you may want to further modify the tool for something else. Let's store the remap values in the point attribute. I'll name mine f at remap_x and f at remap_z. Let's put down an output, go up one level, and see if everything is working. Let's increase the number of points on the line so we can see the remap values. And looking at the geometry spreadsheet, they are working. Even when I increase the length of the line, the remap value stays the same. So everything is working great so far. Now for our next step, let's calculate and store each point's radius, azimuthal angle, and polar angle. Drop down another point wrangle and rename it to get spherical coordinates. As shown in our illustration from before, we are going to let x be the polar angle, z be the azimuthal angle, and y be the radius. Let's create two sliders, max degrees x and max degrees z. This would allow us to determine what is the maximum degrees of rotation to remap to if we don't want the effect to only act on 0 to 360 degrees, but maybe something smaller, and this adds a certain level of control and flexibility to the tool. We then multiply these max degrees with our previously calculated remap values. This would give us the amount of rotation for each point. For the radius of the circle, we are going to clamp the y values again between two sliders, so the user can customize it however he wants. The general idea I had for the tool's default is that when p.y is 0, radius is 0. As it goes up, the radius gets bigger, and if the clamp value for the minimum is negative, the circle gets inverted. Let's drag our sliders into our subnet so we can control the values from the outside. Just going to clean up the UI a little bit and giving them proper names and folders. Now for testing, let's just set the angles to 360 degrees and the max Y be 99,999. Let's also lock the range of our rotation in our UI to 0 to 360 degrees. Now, our next step would be to use these values we've calculated before to plot our points on a circle. With that, we are going to use quaternions. So a rotational quaternion is a vector 4 that consists of the vector to rotate around and the amount to rotate around the vector. This is pretty handy as we don't have to worry about which planar axis a point ends up in. So back in Houdini, let's drop down another point wrangle. Call it polar coordinates by quaternions. So first we want to generate a quaternion, which consists of the axis of rotation and the amount to rotate. Looking at our viewport, the axis we want to rotate about is the z-axis, as you can see when I drop down this transform node. So let's make our axis 0, 0, 1. Our rotate angle is then the radians of our angle A. We have to convert our angles to radians for the functions in Houdini to work. Now let's create a vector for, call it rotate quad, and use the quaternion function to generate our quaternion. We input our rotate angle and our axis, and we have our quaternion. As simple as that. The next thing we want to determine is our starting axis. In this case, as we are rotating around the z-axis, we can have our x-axis be our starting axis. You can use the y-axis if you so wish to, but I'm going to use the x-axis. We can now use the qrotate function, which rotates a vector with a quaternion. Using our starting axis and our calculated quaternion, this will return us the resulting rotated vector. As the vector is still a unit length and just tells us how much the rotation is, we can multiply by our radius, which represents the magnitude of the vector. We now have our calculated x, y, z coordinates using our custom polar coordinates remap. Let's drop down another point wrangle to give us the ability to blend the points from its current position to our newly calculated position. We create a vector variable which holds the current position and a polar vector which holds the polar x, y, z position. I'll just put them in variables so it's easier to read the code, at least for me. We create a slider called bias, and then we use the lerp function to do a linear interpolation between the current position as well as our calculated polar x, y, z position based on bias. Let's add the bias to our UI. And now let's animate our line going upwards by Alt left clicking on the transform Y value in frame 1, go to frame 60 and keyframe the transform Y to 1. Let's crank the bias to 1 and watch what happens. We just recreated the effect in After Effects. And as we play with the sliders on what is the max rotation, we can see everything is working well. Now let's transform our line to have some depth so we can get started on calculating the spherical coordinates transformation. Drop down another point wrangle, and first and foremost, we need to determine our rotational axis. At the start, we were just working with a 2D circle. At this stage, our axis of rotation is our z-axis. In this case, I drew it facing upwards so we can better visualize it. So when we rotate the purple line according to our azimuthal angle, our plane of rotation is different now. The rotation is taking place in a new unknown axis. So that is why we must first find out what is this axis in order to create our rotation quaternion. We have our polar xyz, which represents our starting line, and the z-axis, which represents the orthogonal axis to the polar xyz. With that, we can calculate the cross product to get our axis of rotation. So back to Houdini, let's implement this. We get our polar axis by normalizing our polar xyz. The z-axis by just initializing the values, and we can use the cross function to get the rotational axis. The rotate angle will be the radians of our calculated angle B, and with both the axis and the angle, we can calculate our quaternion. Now for our rotation, like we have before, our start axis would be where we end off after our polar transformations. We rotate it with qrotate and multiply the resulting vector with our radius. Let's add in another blend, copy and paste the values, and do a couple of renames. Let's also add a switch node, so we can control if we want to use the polar or spherical mappings. We can update the UI by adding a toggle to control it. So let's see what it gets us. It looks a little strange using a line, but to visualize it better, let's use a grid. And we can see how the grid is wrapping itself into a sphere, which means the tool is working. Now let's do the last few tweaks to the tool by addressing the UI we've created right at the start of the tutorial, the min and max values. We'll modify the ranges of our max and min y first. And now let's add the functionality to choose to remap based on the min and max or a specific range specified by the user. Let's create some min and max sliders and remap the x based on this min and max values. Do the same thing for the z-axis. Now we check which remap the user wants by checking if the checkbox has been ticked. In the VAX code, I'm just going to create two integer sliders to check. If it's 1, or if the checkbox value is ticked, we remap by value. If not, we remap by the point's min and max position. And now let's create the sliders and link to our UI. I went ahead to create some examples on how we can use the tool. But before that, let's fix a little error. Well, I was copying and pasting. I forgot to rename this to remap z_value. So I'm going to correct that real quick. Alright, so Entagma created this tutorial a year ago about Rayleigh-Taylor instability. If you guys haven't checked them out, you definitely should. They create really amazing videos and tutorials. I've posted a link to the tutorial in the description below if you guys are interested. Anyways, they have provided the scene file, and what I did was downloaded and copied the setup, modified it slightly, and try to test it with the tool. So I created some depth to the box, so we have some Z information, or Z information. I scattered some points, and the rest is the same. And what we have is a pretty looking fluid. So using the tool we've created, we can see everything is working. And when we move the sliders, you can see we can create some pretty interesting effects, like blooming, folding, and some interesting patterns. This could be pretty useful to create some abstract evolving effects. We can even just rotate the points by a 90 degrees and use the mirror node to create some symmetrical patterns. Finally, I'll show you how I created the video at the start of this tutorial using the tool we've created. I first started off with a grid and gave it some normals pointing upwards. I find the center point of the grid, and I have some color value pulsating from the middle of the grid. Using our tool, I made the maximum angle in the X direction 90 degrees and animated the max X to give this kind of stretching effect. I then mirror it to get some symmetry. To get the same number of points throughout the animation, I create another high poly grid, and I did an attribute transfer to transfer our CD and our N attributes to this high poly grid with consistent number of points. I then scatter some points based on the color value, or CD, and I create some velocity by multiplying the normal with a slider speed. Oh, and I have to mention, in order for the velocity to work, I did a slight modification to our tool. In our tool, not only did I rotate the position, I also rotated the normals based on our rotation quaternion. And if you visualize the normals, you can see them pointing in the direction the colors are moving. This allows me to use the normals as the velocity. So with the points and velocity, I created some density and just threw it in the pyro solver. I didn't do much to the pyro, just added some temperature based on density, added some gravity, some turbulence, disturbance, and dissipation. Most were just the defaults, and it is the calculated velocity, as well as the temperature and buoyancy that created this pyro effect. I also added a collision sphere so the smoke stays inside an orb-like shape. I then retimed the smoke and remapped the values to create the tutorial video. I later went a step further and used the unretimed smoke to evac our particles. Again, using our tool, I remap and animate the points using the spherical coordinates to give this sort of evolving effect. I then use the points and plug it into another pyro simulation. And this is the results it produced. So that's it for this tutorial. I hope it has been useful. And if there are any comments or suggestions on how I could improve the setup or the tutorial, do let me know. I'll put the link to the tool we've created on Gumroad if you just want to get your hands on the tool itself and not bother with the setup. A special shout out to two of my colleagues, Simeon and Faiz, who gave me some compositing tips to make the video look a tad better. Thank you for watching and have a nice day.